Hi, everyone. My name is Mojgan Navardi, and I'm a graduate student in the Electrical and Computer Engineering Department at Johns Hopkins University. Today, I'll be presenting my research on meta-reasoning for efficient dynamic model selection, particularly in the context of resource-constrained AI systems. This work is part of an ongoing effort in our lab EHPC under the guidance of my advisor, Dr. Tanush Mosanen. I would also like to acknowledge and thank the EHPC lab members for their support and insightful discussions that contributed to this research. Artificial intelligence is increasingly deployed across a wide range of domains, including healthcare, autonomous systems, and industrial automation. In these critical domains, making fast and accurate decisions is essential. While cloud-based inference is often preferred due to its high computational resources, there are significant advantages to deploying AI models at the edge. These include reduced dependency on cloud infrastructure, lower latency, and enhanced data security. However, both cloud and edge approaches face challenges. Cloud-based solutions raise concerns about communication delays, energy consumption, and security, while edge devices are constrained by limited computational power and resources. These trade-offs motivate our approach to adaptively allocate computational resources based on task difficulty, thereby leveraging the strengths of both cloud and edge environments. This slide illustrates a motivational example drawn from autonomous navigation scenarios. In these systems, if we rely solely on cloud-based AI, especially for tasks like large language model inference, we run into issues when wireless signal strength weakens. As shown in the top graphs, lower signal strength leads to more packet loss and a clear increase in latency. In configurations 2 and 3, where inference is done in the cloud, we see that energy consumption and latency increase significantly when the connection weakens. Config 3, in particular, demonstrates the highest energy cost and latency under weak signal conditions. In contrast, Configuration 1, which uses an edge-based LLM, maintains both low energy usage and low latency, regardless of connectivity. This highlights the value of a hybrid approach, where the system can intelligently switch between edge and cloud processing depending on current conditions. This ensures that even in connectivity-constrained environments, we can make timely, energy-efficient decisions, a critical requirement for autonomous systems operating in real-world, dynamic settings. The core challenge I aim to address is how to effectively switch between different models in response to environmental changes within resource-constrained systems. Given a pool of models with varying complexity, the goal is to decide, based on factors like connectivity status and task difficulty, which model offers the best trade-off between performance and cost, under real-time and power constraints. Here, performance refers to accuracy and success rate, while cost refers to power consumption and latency. To effectively switch between different models, meta-reasoning offers a flexible approach for dynamic and uncertain environments compared to fixed, predefined strategies. Meta-reasoning refers to an agent's ability to think about its own thinking. It involves 3 levels: the ground level, which is the execution or doing phase; the object level, which includes the algorithms, in our case, different models; and the meta level, which oversees the entire process, acting as a higher-level monitor. This slide presents our meta-reasoning-based framework for multitask autonomous navigation using large language models, LLMs. We propose a LLM-based dynamic planning framework that can handle abstract, high-level tasks. The system takes a complex instruction and uses an LLM to break it down into a sequence of executable subtasks. As shown in the example, an abstract command like "follow the boxes in the sequence of red, blue, green, and finally the ball" is passed to the LLM. The LLM interprets this command and outputs the correct order of subtask IDs. Each of these subtasks is handled by a low-level reinforcement learning (RL) policy, in our case, a DQN policy trained to navigate to specific objects identified by their bounding box coordinates. The architecture is divided into 2 layers: the high-level policy, where the LLM selects the next subgoal based on the abstract task; the low-level policy, which uses object detection via YWLOV8N and sim-to-real transfer techniques to carry out the navigation for each subtask. In the case study shown here, The environment includes multiple rooms with colored boxes, and reaching the ball is considered the final goal. The LLM dynamically adapts based on which objects are detected and plans accordingly. Importantly, this framework is generalizable and can be extended to a wide range of multi-step, goal-driven robotic tasks. This slide showcases our approach to language-guided navigation using reinforcement learning. We adopt the idea of a hierarchical agent to split the navigation task into two levels: a high-level controller that interprets the language-based goal, a low-level policy that handles actual movement and obstacle avoidance. One of the key benefits of using RL in this context is that we can deploy lightweight models suitable for real-time navigation on edge devices. However, a major challenge is the sim-to-real gap. Models trained in simulation often perform poorly in the real world. To address this, we introduce a pre-processing module that helps bridge this gap. Specifically, we use YOLO for object detection and extract bounding box coordinates, which are combined with LiDAR-based collision avoidance signals. These are then passed to a Deep Q network, DQN, policy for decision-making. The system has been tested in complex environments, and we achieved a 98% success rate in navigating to the correct object, even when guided by abstract goals like go to the red ball. The visual here shows the real-world test setup, and the block diagram highlights the architecture. You can see how image and LiDAR inputs are processed through separate modules, then merged with sub-goal information to generate the action. This slide showcases all the boards and hardware used for real-world implementation and hardware measurements. It shows demo on obstacle detection and object detection with my squeezed edge YOLO models. Also RL navigation to reach the goal. On the right side, you can see the power measurement setup used to evaluate energy efficiency and inference latency during experimentation. This slide shows two case studies of model optimization. On the left, the bar plot shows I reduced the model size by 14 times and 12 times, which can fit on a variety of resource-constrained edge devices, including embedded CPUs and GPUs, as well as tiny drones that has only 500 kilobyte memory. I deployed a collision avoidance model on a tiny drone with only a few kilobytes of memory. The drone was able to avoid obstacles successfully in real time, while consuming only 850 milliwatts. On the right, I achieved an 8 times model size reduction for Edge YOLO, which was published in IEEE Transactions on Intelligent Transportation Systems in 2022. The image and video show how well the optimized model works for detecting humans and shapes, using a dataset that I collected myself. This slide presents the results of the proposed meta-reasoning-based cloud edge switching method, published in the IEEE International Symposium on Circuits and Systems. To begin, I collected offline data on power consumption and communication latency, and then designed a meta-policy dynamically switch between cloud and edge models. The plot on the right shows a comparison. The red curve represents a cloud-only approach, which fails to meet real-time latency constraints. In contrast, the meta-policy successfully completes the mission while satisfying latency requirements. Here, you see a demo of both cloud and edge deployments for obstacle avoidance. The right video shows the cloud-based implementation with live video streaming between the drone and the server. You can observe the probability rising above 90% when an obstacle is detected, demonstrating accurate and timely inference. I proposed a meta-reasoning framework that leverages a large language model, LLM, for dynamic planning, enabling an agent to autonomously navigate and reach goals in its environment. In practice, meta-reasoning dynamically switch between config 2, cloud, and config 1 onboard for tasks like robot navigation. In the chart, the baseline red plot relies on cloud computing alone, as network strength, blue plot, weakens, energy consumption spikes. Meanwhile, meta-reasoning green plot keeps energy usage in check, up to 4 times more efficiently by switching at the right moments. For example, config 1 might draw 10 joules on board, while config 2 can be as low as 4 joule with a robust signal but can skyrocket to 40 joule when the signal is weak. To summarize, my focus is on meta-reasoning for efficient dynamic model selection in resource-constrained AI systems. I began by applying model reduction techniques to significantly shrink model size, This model zoo serves as the basis for selecting the most appropriate model using a meta policy. To guide this selection, I introduced a reward function for training the meta policy. Finally, this policy will be trained in an interactive environment to enable adaptive model switching in real time. Thanks for your attention.